And then I pass over to Professor Thomas Maschmeyer, who is our host today. So I welcome everyone to the last Sydney Nano Distinguished Lecture of 2020. I begin with paying my respect to the first custodians of country throughout New South Wales, in particular on Gadigal people of our nation, the traditional owners of the land on which the University of Sydney is built. I pay my respect to their elders, past, present, and emerging. I pass the floor to Professor Maschmeyer to introduce our distinguished lecturer today. And with that, I hand over to you, Thomas.
Yeah. Thank you very much. It's a great pleasure to introduce the Sydney Nano Distinguished Lecture of Professor Linda Nazar from the Waterloo Institute of Nanotechnology. And looking at the bio, and of course I'm already aware of the fantastic science anyway, but I see that in 2020, despite COVID, it wasn't a bad year. So she won the Materials Research Society Medal, which is very prestigious indeed, and was inducted into the Royal Society as fellow. And normally one needs to win the Nobel Prize first as a non-English citizen. So I think we may hear more in the near future. So I'm very much looking forward to this lecture, and it's really about, I think, the future of batteries and energy storage devices, and that future undoubtedly lies in the structure of nanomaterials and in the interface and the interfaces. So I'm really looking forward to this talk, and I'd like to welcome Professor Nazar and give her the floor.
Well, thank you very much, Professor Maschmeyer, for the and the University of Sydney Nano Institute for giving me the opportunity to present our work. I might start by actually congratulating you for winning the Prime Minister's Prize for Innovation in 2020. That was tremendous, and of course for your startup company, Jillian. So you're absolutely right. I'm going to be not really talking about unraveling complexities at the nanoscale. I'm going to be more talking about nanomaterials and how they can transform our world. But I mean, with respect to energy storage. But first, let me just remind you that materials in the 20th century was really governed by technological challenges, whereas materials chemistry in the 21st century is, of course, about food, water, diseases, and climate change. And that was mentioned by George Whitesides back in Angewandte Chemie in 2003. And so there's a lot of different material solutions that one can imagine to this, some of which are listed here. And of course, electrochemical energy storage is one of those. And so nanotechnology, I always have trouble figuring out exactly what this is. I'm actually in a chemistry department and in WIN, and we're always struggling to define nanotechnology. But I'll be talking a little bit about innovation in energy storage, both through nanomaterials and control of these interfaces at the nanoscale. And basically, trying to take us from the Volta battery to a very modern day battery. And what one has to remember is, I think, that all electrochemical energy storage relies on mass transport of ions and electrons. And these are facilitated at the nanoscale. But there's also either a liquid or, as I'll be discussing shortly, a solid electrolyte. And this is in contact with both electrodes. And especially for liquid electrolytes, degradative reactions of the electrode with electrolyte are also enabled when one uses nanomaterials. And so you can solve problems of mass and electron transport with nanomaterials, but you have sometimes degradative reactions to deal with. So it's not a complete silver bullet, as virtually nothing is. So I would also like to remind you that there are a lot of diverse batteries that are needed, and they can obviously be used for exploiting renewable energy resources, for powering the world, enabling low-cost vehicular transport. And the energy scale in which these energy is stored ranges from the watt-hour to the kilowatt-hour to the megawatt-hour. And so that means that these diverse energy needs, which also encompass lightweight batteries, compact batteries versus, for example, long cycle life batteries, need diverse materials with different cost points. And I'm with the Joint Center of Energy Storage Research in the USA. We have a multi-million-dollar enterprise in energy storage, and everyone got together and wrote this article in BNAS, which is talking about how these storage needs are emerging. So today I'll present 3 vignettes, a very short one on grid storage involving aqueous zinc ion batteries, a little bit on lithium sulfur batteries that are lightweight, enabling electromobility for flight, and mostly focus on some of the solid state electrolytes and batteries that have encompassed our attention for the last couple of years. So I'll start with the electric grid. I don't probably think I need to remind you that intermittent renewables need energy storage to feed back to the grid and also to charge electric vehicles. And they allow one to have dispatchable power. And as you may also know, the levelized cost of energy for renewable plus storage is actually falling faster than either alone. And so this, what's sometimes called plus storage, is actually moving beyond the first adopters. And these first adopters really tend to be lithium-ion batteries of more traditional type. There's some Tesla cells in South Australia, picture of these. There's another Tesla pack installed in California. And there's plans to replace gas plants with big battery projects. And this is important as first adopters of technology for lithium batteries. But non-aqueous lithium-ion batteries are certainly not necessary, even though these are sort of starting the wave. And of course, redox flow, vanadium redox flow batteries have been around for a long time. So I'll just mention a few things about our zinc ion batteries. And one might ask, why zinc metal? And of course, this started off the Volta pile or peel in 1800. And the point is that zinc is stable in water. It actually has high volumetric energy density. I feel like I'm taking coals to Newcastle because I'm sure you know all about zinc batteries in the University of Sydney, but anyway. So for those who may not be familiar with this, zinc is obviously high abundance, it's non-toxic, and especially it has a small exchange current for hydrogen evolution and a large kinetic window due to this overpotential for hydrogen evolution. So this is kind of the functioning window if we put everything with respect to lithium, which I always do, that allows us to work with, that allows us to function in a zinc ion cell and use a zinc anode. And of course, an aqueous electrolyte. So this is a nice environmentally benign alternative, at least in principle. So our adventures in this were not in zinc air batteries or zinc bromide batteries or others, but we tried to develop an intercalation battery that was similar in its function as a normal lithium ion cell, where there is the intercalation of lithium ions in and out of the positive electrode. And we did this by creating nanofibers of these layered vanadium oxides. It actually has a little zinc in it to start, but it has this vanadium oxide sheet structure that is shown here with just a little few zinc ions to start off with between the layers. And the point here is that these nanofibers are very thin and very long. So they have a very high aspect ratio. And they're only about 200 nanometers wide by about 50 nanometers thick. And this is important because this cell relies on the incorporation of zinc into this already slightly zincated material, in which a lot of zinc is incorporated. And it does so by pushing out some of the water between the layers. We call this a water-assisted process. And it kind of functions like an accordion. So when you put this material, these layered ribbons in water, effectively the water puffs up the layers. It allows the zinc to incorporate between them. And as the zinc incorporates between the layers, the accordion sort of pulls shut until finally we have complete discharge of the cell, and on recharge, the same process, the reverse process rather, occurs. So the water actually assists, at least in the initial stages, to allow the migration of zinc between these layers. And this expansion contraction is important. And the fact that we are working with a nanostructured material allows that to occur more readily than it would in the bulk. And in fact, when we've tried to make systems that rely on a bulk material such as this, it really doesn't work very well at all. So we often plot things in what we call a Ragone plot, which is just energy versus power. And obviously where you want to be is at very high power and obviously very high energy. So this is a desirable part of the Ragone plot to be in, and this just compares our material, which is this zinc vanadium oxide shown in red, with another common material, which is alpha MnO2, which is almost in a pre-commercial stage, with this Prussian blue material, which has been commercialized, or they're trying to commercialize it out, and Stanford University with a company called LIMO. So we're able to obtain very high capacity. Obviously, the metrics are very good here, and also very high capacity with very stable cycling number. This is probably not as stable as a lot of zinc bromine batteries, but for an intercalation battery, it's very stable. And the raw materials cost is really fairly low. So the estimated energy density that we've calculated, or on the basis of a lot of spreadsheets, is around 400 watt-hours per liter. And that's only half of what lithium ion is at 800 watt-hours per liter. But the point is that these materials can be stacked much more readily than a typical cylindrical lithium ion cell. So this is just at the cell level. This isn't at the pack level. At the pack level, we anticipate much better metrics. And so we originally published this paper in Nature Energy. We followed it up with sort of more fundamental work and also a review article in Joule. And since this zinc ion battery that we published in 2016, as a whole, the field is now up to about 640 citations per year. So there's promise, I think, in this area. So then now I'm going to switch to advanced batteries for electric mobility. This is just an article from The Economist in 2019, again, telling you probably what you know already, which is that car makers are placing a lot of effort in battery power. And this is predominantly because of, well, many reasons, CO2 emissions being one of them. But also the fact is that an internal combustion engine has hundreds of moving parts, whereas an electric motor just has one. And that means that its efficiency is much higher than the typical internal combustion engine. And so this gives rise to, you know, pretty desirable fuel costs. And for example, by 2040, Norway is planning to have all of its short-haul commercial flights be electric. So there's a lot of opportunity here. And the question then is, how do we move into next generation systems? So this is the classic lithium-ion battery that you all probably have in your laptop. It contains a graphite intercalation anode, which is a layered material and which can incorporate lithium. And today's batteries will have a little silicon in them, as nanosilicon, to increase the capacity. And to the positive side, the cathode, as we call it, it's also an intercalation material with lithium ions in between these oxide sheets. And so, of course, the lithium ions go back and forth across this organic liquid electrolyte as the battery is either discharged or charged. And so it is anticipated that in the coming 5 years, perhaps longer, depending on how things move along, that the negative electrode will be replaced with lithium metal. The positive electrode may be replaced with conversion materials that don't operate by intercalation, but this conversion reaction shown here. And that will necessitate new organic electrolyte or just new electrolyte concepts. For example, sulfide ionic liquid electrolytes that I'll be briefly touching on, and also solid state electrolytes. And if one can actually successfully implement a lithium metal anode, then never, even without considering alternatives at the positive electrode, the predicted energy density of lithium ions is more than doubled. So if we just look at a typical sort of MESA or standard graphite, this is a metal oxide called 622, and this is in the Tesla. So if we take that and we replace the anode with lithium, already the energy density is doubled without really doing almost anything. This is techno-economic modeling on the part of Kevin Gallagher, who was at the Argonne Labs. And lithium sulfur batteries require a lithium metal anode because the sulfur at the positive electrode has no lithium. And so you can see there's a variety of different estimates for what this power would be, or that the energy would be either in the pack level in terms of volumetric versus gravimetric energy density. And finally, a negative lithium electrode is required for all solid state batteries. It does come with the tremendous disadvantage or problem of dendritic growth. And this actually shows a real image, a photographic image of such dendrites, which grow from the anode to the cathode. And ultimately, if they pierce the separator, of course, they cause runaway and serious safety issues. So a lot of the problems with all of this new technology is trying to control the lithium metal anode. And it's not necessarily, or dendritic growth, and it's not necessarily solved with a solid electrolyte, as I'll mention later. So I'll start off by talking about lithium sulfur cells. So sulfur is a very low cost element. It's $170 a ton. There's about 5 billion tons in the world. This just shows some sulfur deposits from the oil tar sands in Athabasca, in Alberta. So it's almost, it's a benefit. And the problem with sulfur is that sulfur batteries, there's lots of problems. One of them is that both sulfur and the other end member of the redox cycle are both really, really great insulators, electronic insulators. So they have negligible electronic conductivity. So long ago in 2009, we developed this nanoporous or mesoporous carbon. You can see these are little carbon rods effectively. And they're on the nanoscale, 10 nanometers or so. And so we arranged these in these little sheaths and then effectively incorporated molten sulfur into this arrangement, this array of carbon tubes. And when the sulfur was just at the right incomplete filling level, it allowed for expansion when one incorporates lithium to form Li2S. And so the point is that you leave a little bit of space for the electrolyte to incorporate into the sheath. And then finally, when you form the Li2S, if you have the capacity, the mass capacity just right, the Li2S is now in close contact with the carbon. And that enables the recharge process, which is shown here. So this was essential to this technology and kind of revitalized the field because it actually worked reasonably well. What we didn't realize at the time was that carbon was really not the ideal host, unfortunately. And this is because lithium sulfur batteries operate on the process of dissolution of polysulfides. So the lithium from the anode gets basically oxidized into the electrolyte, and the sulfur at the positive electrode gets converted into polysulfides. And there's a whole sequence of sort of a chain of command as one goes from sulfur, which is insoluble, to Li2S, the end member, which is also insoluble, but the intermediates are quite soluble. And this is sometimes referred to as cheese to milk back to cheese conversion because of this solubility problem. And it really is a problem because the dissolved polysulfides drift back onto the lithium metal anode, whereupon they become chemically reduced and ultimately passivate the negative electrode. And they also result in self-discharge, which reduces the Coulombic efficiency. So while this has a really tremendous theoretical capacity, both in terms of gravimetric and volumetric, the practical capacities barely reach 1,000 milliamps per gram, which is kind of a metric. It's basically coulombs stored per gram. So since the paper long ago, there has been an awful lot of effort, both by us and many hundreds of thousands of groups around the world. And so I can't summarize them all here. We did write a review article on it. And this just shows a few examples from our group. And really one can sort of divide the issues at the cathode to developing better surface chemistry to control this polysulfide dissolution, improving the electronic conductivity of the cathode to allow for high rate capability, improving the architecture with binders to effectively allow for this elastic expansion contraction, using computation to try to guide new materials for the cathode, and especially electrolyte optimization, which is necessary in order to sustain the negative electrode and also to solve the problem of high electrolyte volumes that I'll talk about on the next slide. So I'll just, the next couple of slides, focus on the electrolyte issue because I don't have time to discuss all the rest of it. So as I mentioned, the polysulfides that are formed in solution go through this cascade all the way from the most oxidized to the most reduced member. And they, in typical solvents, which are dimethoxyethane dioxylane, they are very highly soluble. And as they form, if they're not constrained in some fashion at the cathode, which is what that sheaf of carbon did, they drift over and, as I said, reduce on the surface of the anode and effectively passivate it and shut the cell down. So the problem is that if you use a high electrolyte volume to solubilize the polysulfides, you end up with really low energy densities, both in the volumetric and the gravimetric level. And really where you want to be is at a low electrolyte to sulfur ratio, upwards ideally here, if one can get that. And that means redesigning the chemistry almost completely. So if one could develop, for example, an ionic liquid that has very limited polysulfide solubility and basically trigger a solid-solid transformation. In other words, going from sulfur all the way to Li2S with very little electrolyte involved, one stands a chance of maybe overcoming this problem. And that's effectively how a lead acid battery works. I mean, not obviously with lead oxide. So our initial attempts finally led us to what we think is a pretty great system. And effectively, we formed a solvate ionic liquid by using a diglyme, which is basically just an ether. But this particular diglyme has just the right length to wrap around the salt anion pair that is used as the salt in the electrolyte. And the point is that as it wraps around this pair, it prevents the diglyme from solubilizing the polysulfides. So at high electrolyte ratios, you can see the intensity of the solution from those dissolved polysulfides. But as you go to high salt and low electrolyte concentrations, there's almost no solubility of the polysulfides. And this is shown by computation carried out by at the Argonne National Labs by Larry Curtis and his associate, Badri Narayan, in which they compared this is using ab initio molecular dynamics modeling, a very high electrolyte or low salt ratio to a high salt ratio condition. So in other words, lots of electrolyte, very, very dilute condition to a very high salt condition. That'd be the easiest way to describe it. And you can see that at the dilute condition, which is here, you have a lot of free diglyme in solution. But when you have a very low ratio, you have the diglyme bound up in the form of these contact ion pairs, effectively forming a nano network of the solvent. And so the diglyme is no longer, as I said, available to dissolve the polysulfides. And moreover, it isn't available to inhibit or to corrode the lithium negative electrode. So when we have high solvent ratios to salt ratio, we see a lot of dendritic growth, we see passivation and basically degradative reactions at the negative electrode. We're depositing on copper here. Whereas when we have very low concentrations of the electrolyte or high concentrations of the salt, we see fairly clean deposition. And this is shown by these stripping plating experiments and by the fact that we have coulombic efficiencies approaching 100%. And best of all, the capacity of real cells is effectively stabilized at these quasi-solid state conditions. So you notice the capacity isn't outstanding. It's not up here at 1,000, but this is, as I said, almost pure solid state conditions. So this gave us certainly some hope. And so then in parallel, we also started working on trying to develop membranes for lithium metal anodes, just sort of as another route to stabilizing the lithium metal. And we developed an in situ approach where effectively metal chlorides react directly with lithium metal to form an alloy. And the reaction here is shown for the reaction of lithium metal with zinc chloride to form lithium zinc. It works really well with indium. And so the point is that this film forms directly on the lithium metal. And the diffusion coefficients of lithium in these alloys are basically the same as that of a superionic conductor. And lithium chloride is formed as a byproduct, which basically increases the electric resistance of the film and allows the potential gradient to develop, which is what's necessary to drive lithium deposition under the film. And if we didn't drive deposition under the film, the lithium would simply deposit on the top and we wouldn't be any further ahead. So these are the two important points, the electronic resistivity of the film and the fact that these films have a very high chemical diffusion coefficient for lithium. And so we can see stripping plating over 700 cycles, which is with low polarization, which is reasonably stable, whereas just on foil, we start to see microdendrites forming after even 200 cycles. And this just shows the lithium that actually is plated underneath this film. So we then extended this concept to more traditional electrolytes, which in this case is lithium phosphate. And it's a well-known solid state ion conductor with very modest conductivity. But the point here is that by adding these precursors to the electrolyte and allowing them to react with lithium, we form an amorphous version of this lithium thiophosphate, again, directly on the surface. So sort of analogous to the alloy, but now we just simply have a solid state conductor. And so we are able to obtain uniform lithium flux. We again plate lithium underneath the alloy. This is all shown in these papers that are cited below. And most importantly, we reduce contact of lithium with the electrolyte because the lithium is plated underneath this film. Whereas in the case of just a simple dimethoxyethane electrolyte, we see a lot of dendritic growth and basically non-homogeneous deposition. So the fact that we can think about forming solid electrolytes on lithium leads us then to the very enticing possibility of all solid state batteries. Just get rid of the lithium, the liquid electrolyte completely. And the reason for that is fairly simple. These organic electrolytes have some serious safety concerns. This shows a picture of happens to be a Tesla battery, but it could happen to anyone, sitting in a parking lot somewhere in China where it literally just exploded. And this is a concern for marine shipping, as recent news reports have indicated. So, and the other disadvantage of liquid electrolytes is the voltage really is limited at about 4.3 to 4.4 volts. So if you can switch this liquid electrolyte for a solid electrolyte, automatically there's improved safety. The cells, this shows sort of how a Tesla is designed with the cells being spaced out. Well, in a solid state cell, you can simply stack these very efficiently, and you can obtain 30% increased energy density without actually doing anything to the cell, simply by virtue of this stacking. And these cells are compatible with next generation chemistries such as lithium sulfur, but also with traditional metal oxide materials. And especially important to us here, they sustain much better low temperature performance because there's no viscosity of the solvent that's involved, but they also have better high temperature performance because, again, flammability of the electrolyte at high temperatures is not a concern. So this just shows a very simple diagram of such a solid state cell where we have a lithium anode, we have some protective interface like I was describing in the previous cells, and then the electrolyte is interwoven both as a separator and in the cathode. So we call this a catholyte because it has the electrolyte and the cathode within it. So this field actually got started a long time ago with the formation of a material, or the discovery of a material called lithium germanium phosphate, otherwise known as LGPS. And this is reported by Ryojo Kano in Japan in a Nature Material article that, oh, I'm sure it's been cited even more times than that by now. So the ionic conductivity was 12 millisiemens per centimeter, and that makes it comparable to these liquid organic electrolytes, which are in exactly the same range. And this is the value that we need for practical cells. And I'm just going to remind you, or perhaps let you know, that conductivity is a function both of the mobility and the number of carriers. And the mobility is a function of what's called a pre-activation factor, and especially important is the activation energy for the process. So when we try to develop new solid-state ion conductors, we worry about minimizing the activation energy for transport and maximizing the number of carriers. Now, the problem with LGPS is that it's not stable with metallic lithium because the germanium reduces, and it's also not stable at high potential. However, there's a really nice paper in Nature Energy from Kano working with Toyota that basically shows the performance of solid-state batteries compared to that of sodium ion, aluminum ion, a range of different cells. And the solid-state batteries are shown here, both at room temperature and also at 100 degrees. And so again, this Ragone plot of power versus energy shows that they're sitting in this very desirable target of high power and high energy. And this has really inspired a lot of work in this field. So currently, according to this well-established research organization, the global solid-state battery market is valued at $32 billion US in 2019 with a tremendous compound annual growth rate. So we've turned our attention first to solid state cells, and to try to make some impact in this field, we've turned away from the traditional, well, traditional being the last couple of years, lithium sulfur cell that uses carbon as the conductive additive in the cathode, to nanostructured vanadium disulfide. And the reason for that is that VS2 is a metallic material with very high conductivity. And we can form this material in these very high surface area, sort of nano flower structured morphology. And this allows intimate contact of this VS2 material with the sulfur. And the VS2 is not just a metallic conductor, but it's also a good ion conductor. So it acts as a vehicle to deliver both ions and electrons to the sulfur to trigger the conversion of sulfur to Li2F. And simultaneously, we get capacity from intercalation of lithium into the VS2. And so we end up with very high aerial capacities, which, at least to our knowledge, are the highest that are reported, and stable cycling behavior. So this cell was just used as a prototype or sort of benchmark, the material that I mentioned many slides ago now, the lithium thiophosphate. And what this did was made us think about why Li3PS4 worked well. As I said, its conductivity is only 10 to the minus 4, but we wanted to understand conductivity, ion conductivity in these thiophosphates a little bit better. And so that drove us to some new adventures in understanding the role of anion dynamics in fast ion conduction. And in fact, our initial studies were on sodium ion materials. This is with a paper with Max Avdiv, who was at the University of Sydney, and it was using neutron scattering that we carried out at ANSTO. And we published this a year ago or so. So the concept of anion dynamics is actually not new. It was long ago suggested, some references way back when, and it was dubbed the paddle wheel effect by Martin Jansen back in 1991. And the point is that the paddle wheel effect was used to explain the sudden jump in conductivity from either lithium sulfate or sodium phosphate at elevated temperatures. So in the case of the lithium sulfate, you can see that as you increase the temperature, there's this massive jump in conductivity. And they discovered that just before the melt was achieved, they seemed to be, it was the concept of the sulfate anions rotating was invoked. And this is invoked even as early as 1980. It was never proven, it was simply suggested. And it's been revitalized more recently with other anions, such as these closoborohydrides and in this perovskite material. So we turned our attention to the thiophosphates to see that if it was actually responsible for enhanced conduction in the thiophosphates as well. And the short story is, indeed it is. So before I explain this, I should just mention what the maximum entropy method is for those of you not familiar with it. It's implemented in software package called dysnomia. And so effectively you obtain structure factors from a Rietveld refinement. You apply this MEM algorithm, and this allows you to estimate non-zero structure factors. This is just a little aside for any crystallographer who's in the audience. And this allows us then to obtain nuclear densities. And it actually recovers structural information due to, they often will lose in powder diffraction. So you end up getting these, what we call maximum entropy method maps. And they're actually very powerful. So this is what you're looking at here. And this is the MEM map for this, these thiophosphate materials. And I show you the gamma phase on the right and the beta phase on the left. So what you're looking at is the nuclear density shown, it's sort of labeled here for sulfur and phosphorus. And this is the gamma phase at an elevated temperature. Let's compare it to the high temperature phase. So even at 200, gamma is an extremely poor ion conductor. And you can see that the PS4 group is effectively completely static. Whereas at the same temperature, well, this happens to be at elevated temperature, but because we had to record at elevated temperature, you can see that the thiophosphate groups are actually rapidly showing, they're showing rapid reorientation. Now, we don't know how fast this is. We can just see that it is smeared out sulfur density is indicated by these green patches. So this is a direct image of this reorientational, effectively motion that is imaged by these maps. And it's correlated with lithium ion conductivity, as I'll explain in a moment. So this then inspired us to try to stabilize this high temperature so-called beta phase at room temperature by incorporating extra lithium into the material. And what this does is it expands the volume and it allows this rotor behavior to occur at room temperature. So you can see the same rotor behavior at 200 degrees versus, or actually 350, versus the rotor behavior now at virtually at room temperature. And the same rotational behavior is responsible for lithium conductivity in that amorphous glass I mentioned. And this was proven by our colleague at Michigan, Don Siegel, who recently published on that, on the glassy Li3PS4 phase. So this is sort of exciting because we can, simply by stuffing this structure with lithium, we expand the volume, we turn on this lithium rotational, this polysulfide, thiophosphate rotational behavior. And so to prove this, we carried out ab initio molecular dynamics, and this shows our snapshots are in 1 picosecond of the motion of, you're showing here just the sulfur. And so this, within this 1 second, the sulfur anions that are in the corners of these tetrahedra move very rapidly. And as the as the thiophosphate rotates, the lithium translates in the lattice, either along the Z or the A axis, the Z or the A axis. And this corresponds to basically 1 hop of a lithium through the lattice. In moments where that rotation is transiently paused in the dynamics, the lithium motion is completely static. So it's correlated with this translation when it rotates, and it's correlated with no rotation, in fact, static behavior when the anion is paused. And the reason for this coupling of the motion of the polyanion with that of the lithium is simply because of the structural effect. As the lithium translates through the lattice, it moves through this little bottleneck, which is a triangular window, and the anion is bound to this edge. So as the anion swings, it opens up this bottleneck, and you can see that that is about a 2 angstrom opening, which is really quite significant. So as it rotates, it opens up the window, and it allows the lithium ions to easily pass through. So this explains the paddle wheel or revolving door concept, and there's more data in our paper that actually shows how the two are coupled. So this then leads to other concepts of increasing cation conduction in solid state electrolytes. And I'll sort of end off in a few concepts then here, including cooperative migration and flattening the energy landscape. And I want you to keep in mind this golf course. This is a Waterloo golf course in the summer, because effectively what we're trying to do is we're trying to reduce the depth of these traps. We're trying to flatten the landscape so lithium ions, just like golf balls, can move around this landscape easily. So in our group, we've looked at many different approaches, not just the paddle wheel, which is sort of how to turn on paddle wheel effects, but also how to design materials that have superionic conductivity, which is defined as greater than 1 millisiemens per centimeter. And also trying to design conductors that have chemical and electrochemical stability. So we've looked at a range of, well, not a range, but we've developed some new superionic glasses, and these allow melt processing. These are lithium oxythioborosilicates, which actually are fairly stable to moisture, which is certainly a benefit. We've also tried to tune a well-known structure called the agurodite, and I'll be talking about that on the next slide. And we've done that either by making the material halide rich, and thus changing the sulfide, which is an S2- ion, for a halide monovalent ion. And that really reduces the interaction of the lithium cation with the anion in the framework. And so the picture of butter is meant to indicate that it kind of eases the transport. And indeed, we've managed to obtain conductivity similar to that material LGPS, in other words, upwards of 10 millisiemens by this approach with very high diffusivities. We've also tuned the agurodite structure by stuffing it with lithium, taking advantage of what we learned with the Li3PS4, and achieve conductivities upwards of 20 millisiemens per centimeter because of the beauty of this structure. And as I said, I'll be describing that in the next slide. So along with tailoring lithium thiophosphate, we've also managed to make materials by scalable solution processing methods. And we've also developed superionic materials as shown here, which also display this paddle wheel effect. And more recently, we've been working on electrolytes that are stable at high potential. So since I don't have time to discuss everything, I draw your attention to a couple of review articles, one of ours in 2018, and a really nice article by Saiful Islam and Christian Mascalier in Nature Materials last year. So I'll just highlight the agurodite and the stable electrolytes in the next couple of slides, just to show you a little bit about how we think. So this agurodite is actually a material which has fundamentally very poor ionic conductivity. And it has an unusual structure, which is comprised of clusters of lithium ions. And I won't get into all the structural details because they're fairly, it's too much detail for such a talk. But the point is that if you start off with this parent material, the lithium is sort of bound up in these little clusters. and it doesn't undergo translational hops from one cluster to the next, which is why it has such low ionic conductivity. If you substitute some of the antimony +5 for a combination of silicon +4 and lithium +1, which is effectively tantamount to stuffing the structure with lithium, now conductivity is in the order of 15 millisiemens and above, depending on whether it's annealed sintered, are achievable. And this conductivity is strictly a function of the lithium content. And the reason for that is that lithium populates a metastable interstitial site. And this forms a stepping stone for transport from one cluster to the next, literally. And that lowers the activation energy for the transport and triggers what we call concerted ion migration, because as one ion moves, it undergoes Coulombic repulsion with the ions in this site, and it literally pushes that ion to the next cluster. And so this is, I think, a very powerful strategy for increasing conductivity, this whole idea of stuffing lattices into metastable interstitial sites. And we're planning to expand on this in the years to come. So the agurite is a sulfide material, and that means, just like LGPS, it's not particularly stable at high potentials. In other words, it oxidizes around 2.7 volts, and all of the sulfides do this. And so that causes a problem for practical solid-state battery implementation. And the reason for that is that the cathodes, if you're not concerned about, if you don't want to use sulfur, and sulfur is fine because that's sort of its limit of oxidation potential. But if you want to use higher potential materials to get higher energy density, these are these lithium metal oxides, you actually have to protect the surface of these materials to protect them to protect the electrolyte from being oxidized at that potential, because these operate at about 4 volts and above. And the other problem is that the electrolyte will also be oxidized by the carbon and at the surface of the current collector. So the sulfides are fundamentally not ideal for catholyte formulations because of that low oxidation potential. What is better are the chlorides. And computation by Gerhard Ceder's group show that they have oxidation potentials upwards of 4 volts, which makes them compatible with these lithium metal oxides. So recently we've developed 2 such materials that have high ionic conductivity. It's not as high as the agurite I mentioned, but it's sufficient. It's above that benchmark of 1 millisiemens with attendant reasonably low activation energies. So I'll talk a little bit now about how we build our batteries, just to end off on some practical things. And this is where the nanoscale becomes important. So in the diagram on the upper right here, what you see are particles of this state-of-the-art lithium, nickel, manganese, cobalt oxide. These are called NMC. This is a high nickel content material, which means it can be used at a fairly high potential. And we have literally coated the material with one of these halides. And it's a little hard to see because I don't have a cross section, but effectively this is on the orders of sort of 100 nanometers of halide coating on the material. So in this cell, we use the agurite that I mentioned 3 slides previous, which has this conductivity of 15 millisiemens, and we use that material as our separator, and we use the halide as the electrolyte in the catholyte along with this positive electrode material. And typically we have about 85 to 15 mass ratio of the cathode to the electrolyte, and we use a typical lithium or lithium indium as our negative electrode. So we construct these cells, of course, in our lab and subject them to a little pressure to get them to work well, and work well they do. So again, this is our best halide. It works, this is the one that seems to work the best. We're using this material as the separator. We've coated our materials by a very simple ball milling procedure, actually hand grinding, quite honestly. And so we're able to achieve excellent power because the cell can be discharged and charged in 5 hours at room temperature. And best of all, we get capacities in terms of milliamp hours per gram that are equivalent to its liquid ion, lithium ion counterpart. So we think this is definitely a step in the right direction, and we can sustain charging up to 4.5 volts without coating the cathode material at all. So this is a bare naked cathode material simply with the halide on the surface, and a typical solid electrolyte as a separator. So with that, I hope I've given you a brief tour of how nanomaterials and why nanomaterials are necessary for advanced batteries, both at the negative and at the positive electrode. I might add that you all use nanochemistry in your lithium-ion cells today without even realizing it, because all of these positive electrodes at high potential operate by taking those organic electrolytes and adding additives that actually polymerize on the surface to prevent degradation reactions of the electrolyte. So effectively, we're just doing more sophisticated things with our solid electrolyte systems. And people are also looking at carbon silicon nanocomposites for the negative electrode. But what I focused on today are the zinc ion battery, where we need nanomaterials to allow water ingress and egress, to allow for high power. I've talked a bit about lithium sulfur batteries, where nanoscale is important, and how interfaces, nano interfaces of the lithium metal can help lithium metal anodes function, maybe not perfectly, but at least get them on the way. So with that, I would like to thank all of my graduate students and postdocs who did the work. They are shown here. I'd also like to thank my collaborators who helped us enormously in all of our work. And this is just a picture of my group and our building. And I'd like to thank all of the funding agencies for their contributions. And thank you for your attention.
Well, thank you very much. That was an absolutely fascinating talk, and it's clear why you became FRS. So wonderful. So now I'd like to open the, can people hear me? I'm not controlling this.
Yes.
Yeah, okay. So now we're going to the questions. I presume there'll be quite a few questions. In terms of managing it, it might be either you unmute yourself or do it via the chat. Maybe if you do it via the chat and I moderate, that might be the best way to go. While you are potentially typing, maybe I start off with a first question, and that is your final example of the solid-state lithium battery, which was very impressive. The slide before that, you were saying you either use lithium or the lithium-indium. So are you in fact plating to avoid dendrite issues, etc.? Are you actually plating behind the lithium metal, as you were saying before in an earlier slide?
Yes, well, that's a great and difficult question. What is, you have to, get all your little dirty secrets. So, so the problem is that, you develop all this work over the years, and then you try to pull it together, and, graduate students who develop one thing have long gone, and it's sometimes difficult to get it all working all at once. So the issue is, when we have these nifty little protective films that we're trying to form on lithium metal, it's still difficult to really sustain high current densities that we need in the solid state cell. So effectively, as a method of cheating, because that's really what it comes down to, if we want to charge and discharge at 5 hours, that means we're really pulling really high current densities. And so lithium metal does not sustain this very well. And you might say, well, all you have to do, shouldn't your solid electrolyte inhibit the penetration of dendrites? And in practice, it probably would, but you have to actually make this electrolyte almost completely dense. In other words, completely compress the grain boundaries, because the little dendrites will actually literally sneak right along these grain boundaries. And we have not yet managed to get 100% dense pellets. And so we simply cheat by, at least in our solid state cells, using a lithium-indium composite, because that is very highly resistant to dendrite growth, and it allows us to sustain these higher current densities. Now, that's not to say that we're stuck there. By no means are we. We will solve this problem, but it's kind of a worldwide problem, not just ours.
Yeah, that's right. But it's wonderful work. I just thought, that was a little thing. Do we have any other questions? Otherwise, if we don't, and I'll wait for another chat to turn up. So in terms of voltage or voltaic efficiency, given that I'm currently still using the old-fashioned, simple liquid electrolyte, how dare I? I know voltaic efficiencies can be an issue, of course, as I increase my salt concentration, and there are a number of concepts of water and salt, for example. So it's sort of, and you showed that early on. But what we find is that we struggle with voltaic efficiencies if we want to get any kind of sensible, usable rates of charge and discharge. Is that what you see in all solid state?
Not, so we look at two things. We look at a round trip efficiency and we look at a Coulombic efficiency.
Yeah.
So the Coulombic efficiency is shown here. And let's see, did I actually plot it on this side? Yeah, so it's actually plotted here. So you can see that the Coulombic efficiency initially is not ideal. We must undergo some what we call modification reactions on those first cycles. But then it settles into very close to 100%.
Yeah.
So, and what you're looking at here is that first cycle where you can see there's just a wee bit of overcharge. And as I said, there's obviously some passivation reactions going on at the electrodes that we don't fully understand. So I would say the Coulombic efficiency is actually pretty good. Now, the round trip efficiency is a question of means that it's kind of the polarization of the cell, and it's completely dependent on those interfacial reactions at both the positive and the negative electrode, and defines the voltage difference between the charge and the discharge. Sorry, the charge and the discharge. And so the short answer to your question is that by using really conductive electrolytes, both for the separator and in the catholyte, we can minimize that polarization.
Okay.
And we also have learned, somewhat annoyingly, that a lot of the polarization problems in the cell are due to this lithium-indium anode, which does not function particularly as well as we'd like. So it's no is the short answer.
Okay, fantastic. Well, that's really good. I mean, that gives me a lot of hope for this to be really successful.
Oh, well, there's lots of other problems too. But yes, it is hopeful.
Stay positive, you know, we're still in COVID times.
Yeah, stay positive, right.
All right, then I think we still have a couple of minutes. So you were saying that the solid state batteries could be placed, could be stacked much more tightly together compared to the Tesla ones. The Tesla kind of batteries, which effectively are just Panasonics, right, put together with systems, they do that in part to deal with the heat management. So yes. If you were to stack it, as tightly as you suggest, then you might have some trouble in your heat management, won't you? Because it's not going to be as good as 100% round trip efficiency. So there will be some heat evolved due to that. So how do you deal with that?
Yeah, that's another very good question. I mean, of course, it's heat management in the Tesla cells, but it's also to a certain extent to prevent runaways so that the cells are not in contact. Yeah. But you're right. I mean, batteries cannot function without heat evolution. It has to, that's part of the system. We don't build battery packs in my group. We just build single cells. I guess it's anticipated that heat management will still be an issue, but by, I guess, the waffly answer is that if you can stack these things into these bipolar plates and basically put a thermal draw in the system, you can get around this. And so there's people that build solid state batteries seem to be pretty optimistic about heat control, but that's not me.
Okay, no problem.
At the single cell level, we have no issues.
Do we have any more questions or any questions from the floor? If I
guess I went a little too quickly, did I?
Not sure. I think maybe it's more of a physics. I don't know. But I mean, this is all remote and it's all different to normal. So
I think we have one question there.
Yes.
Do you want to unmute yourself or?
Yeah, so I really like your work about the zinc-ion battery. Currently, many people mention that the zinc metal in neutral will be a very major limiting factor for the application because the dendrite formation of the zinc metal in neutral will be very problematic. How is your view? Have you done some work in that area?
That's one of the things it's a good question as well. That's one of the things we're actually tackling now. One can control that dendrite growth to a certain extent with additives, and that's what people have used for a long time. And you may be aware of hyperdendritic growth, which was published recently by Dan Stangard, and where they were really able to limit dendrites by effectively tuning the morphology of the zinc metal anode. And Deborah Rollison has recently published on a similar concept just a couple of years ago in Science, where they use these hyperdendritic foams in order to control dendrite growth. So that reduces the overall volumetric capacity because you don't have a zinc plate anymore, but it does address, at least at reasonable current densities, that problem. So that's one way to go if one is not going to work with additives, which is, I think, probably a more promising approach. Does that answer your question?
Thank you. Yeah.
Okay, then just remains for me to thank you again for an absolutely wonderful and inspiring lecture. Wishing you well in cold Canada, and you know, good luck getting through the COVID pandemic. And I'm sure that once your spring arises, there'll be vaccines galore, and the world can return back to normal. So thank you very much again for your time and your most inspiring chemistry, for which you need to be congratulated by all of us. So, so virtual or real clap. Thank you very much.
Well, thank you very much for the kind introduction and for the kind ending, and for the invitation, as I said, to speak. And congratulations to you all on your Sydney Nano Institute, and I hope to be able to visit someday soon.
Wonderful. Looking forward.
Okay.
Bye-bye.
Bye-bye.
Thanks,
Bye-bye.
everyone. Thank you.
Thanks again.
Bye-bye.